Hello Year 7, please complete today's Do Now task in your books. Pause the video and complete these 3 questions. Here are the answers to those 3 questions for your Do Now. Today's title is The Conservation of Mass. Please write this at the top of your page. So where have you heard this word before? Conserve. Take a few moments, pause the video and think about where you may have heard this word before. So, you may have heard about it when we talk about animal or plant conservation. You may have heard of the jam conserve. Conservative or conserve means to be adverse to change, and it's very similar to the word preserve. The law of conservation of mass tells us that atoms cannot be created or destroyed. And this means that the mass of the reactants in a reaction must be equal to the mass of the product, because it's got the same number and type of atoms at the beginning as there is now at the end. They've just been rearranged. So, let's have a look at this question. So both Abby and Jane have a beaker of water and a beaker of sugar, and they are put on both sides of this set of scales. And as you can see, they are balanced. Jane takes her beaker of water off the scales and pours her sugar into her glass. She stirs it until she can no longer see the sugar granules. Abby leaves her water and sugar alone. In your books, can you draw what you think the scales will look like if Jane puts her beaker of dissolved sugar water back on the scales? She's also going to put the pot that the sugar was in back as well. And then have a go at explaining your answer. Pause your video here and have a go at this question in your book. This video will help explain the answer to that question.
A simple example to understand the law of conservation of matter. First, we'll start by weighing out 25 grams of sugar. Perfect. Next, we'll weigh out 150 grams of water. These scales are set so they don't weigh the weight of their containers. We want just the weight of the sugar and the water. Yes! Now we simply mix the sugar into the water. Here you go.
It looks like the sugar disappeared.
But it just dissolved, right? The sugar's still in there.
Well, what evidence do we have that it's still in there?
We can weigh it. If it weighs 150 grams, then that means the sugar's gone.
And if it weighs 175 grams, it means the sugar's still there.
Let's try it.
175 grams. That's the weight of all the water plus the sugar.
Even though we can't see it.
The sugar is still in there. It didn't disappear. The law of conservation of matter tells us that matter never just vanishes. Hey kids, you up?
So, that video helped us to know that if we look at this question again, even though Jane has now mixed her sugar in with her water, the scale should remain balanced because she has not changed the mass. The sugar is still there, even though she won't be able to see it anymore. So, the mass of her water plus sugar will be equal to the mass of Abby's water plus sugar. So, when solids and liquids are mixed together or they react, the mass stays the same. But how about gases? Do gases have mass? And if so, how could I weigh a gas?
Air is the most common gas of all. Blow into a balloon and it easily inflates. The question is, will a full balloon be heavier or lighter than an empty one?
This one is definitely the heaviest.
I think this is the heaviest one.
This deflated balloon has a mass of 2.1 grams. Inflate it, and how much do you think it'll weigh? It now has a mass of 2.6 grams. Each tiny air particle in the balloon has a mass. One particle on its own doesn't weigh very much, but a balloon contains many millions of them. So a full balloon always has more mass than an empty one.
So, this means that we have to consider gases when we are looking at the conservation of mass, because although it's very small, gases do have mass. So, if we can't contain the gas in a balloon or a flask with a stopper, then we are not actually including the weight of all the reactants or all the products in our reaction. And this is what happens. So, someone's got some vinegar and some bicarbonate of soda, which you might use in baking at home. And they weigh 219.4 grams, including the beakers. Now they are adding the two reactants together, and a reaction is happening. We know this because there's fizzing. The fancy word for fizzing is effervescence. As you can see, the more the reaction occurs, the lower the total mass of the things now on the scales. So this looks like our products weigh less than our reactants. But actually, it's just because we're not measuring the mass of the gas that was released. That gas was carbon dioxide, and that's why we got the fizzing. So, when a gas is formed as a product, it may appear that the mass has been lost because we no longer include the gas when we do our overall mass measurement. And the only way to get round this is to capture the gas that we create, either by using a balloon or by putting a stopper on the top of our reaction vessel. This can be seen here.
If I mix vinegar and baking soda
So,
together in
this man
bottle,
is doing the exact same experiment as you saw in the video before, but this time he is going to use a balloon. So first of all, he pours the vinegar into the bottle.
Then I'll add a tablespoon.
Then he adds the baking soda to the balloon. This helps make sure that none of the reaction happens before the balloon is on top of the bottle ready to collect the gas. By putting the balloon over the bottle, we create a seal so no gas can escape. So we go from a very empty balloon to a now inflated balloon. So if we'd weighed the bottle and the balloon containing the baking powder before, and we now weighed this, it would be the same, because we have collected that gas that was that extra product that we didn't weigh in the video before. So, that was gases as a product, but some reactions have gases as a reactant. So the mass of the gas is not included in the beginning, and this means that it appears the mass has increased during the experiment. An example of this is when we burn steel wool.
Welcome to Moo Math and Science. In this video, I'd like to investigate the question: when you burn an object, does it gain mass or lose mass? I will burn some steel wool and see what happens to the mass of the steel wool as it burns.
Okay, so let's go ahead and light the steel wool, and we'll let it burn for a bit. And while we are letting it burn, we are going to very carefully keep an eye on the mass. And right now the mass is 154, and it's burning. And again, we will keep an eye on the mass. It is still 154. I'm going to move this back just a little bit so you can see the mass. And now, if you'll notice, the mass is now at 155, still burning. Okay, the question is, why is it when you burn steel wool, you would think as it's burning that the mass would go down, but in fact the mass is going up to 155.
Okay, so during this experiment, we've taken some iron wool, which is just iron stretched out into really thin threads, and we've burnt it. And during that combustion, which is the scientific word for burning, it's reacted with oxygen, and that to form iron oxide. So that oxygen is now bound to the iron and is now a solid. So we can measure the mass of it. But at the beginning, we did not measure the mass of the oxygen in the air, and that's why the overall mass appears to have increased. In summary, can you fill this out in your books, please? So pause the video and see if you can complete these 3 sentences. There is then a worksheet for you to complete. So 10 grams. I'm going to do the first example with you, and then you can have a go at the rest on your own. So 10 grams of magnesium ribbon is burnt in oxygen. What happens to the mass? So if it's burnt in oxygen, that means oxygen is a reactant. And we won't have measured the mass of the reactant at the beginning, but we will be measuring the mass of the oxygen when it's been reacted with the magnesium at the end. So that means that our mass will increase, and the explanation is because we will now be including the mass of the oxygen in the product weight, but we did not include the mass of the oxygen in the reactant's weight. So have a go at the rest of this worksheet, and please upload all your work to Teams so that I can give out some R points, and I look forward to hearing from you soon.